us at +1 678 648 4277. You can mail us at info@architectureassignmenthelp.com or reach us at https://www.architectureassignmenthelp.com. Part C, Vliw machines. In this question, we will deal with the following C code sample on a Vliw machine. You should assume that arrays A, B and C do not overlap in memory. Our machine will have 6 execution units, 2 ALU units, latency 1 cycle, also used for branch instructions, 2 memory units, latency 3 cycles, fully pipelined. Each unit can perform either a store or a load, 2 FPU units, latency 4 cycles, fully pipelined. 1 unit can perform FAD instructions, the other FML instructions. Our machine has no interlocks, so the programmer has to make sure that appropriate data is in the registers when an instruction to read it is issued. Assume that the latency of each execution unit includes writing back to the register file. Below is a diagram of our Vliw machine. architectureassignmenthelp.com. The C code above translates to the following instructions. Question 6 Table C1 on the next page shows our program rewritten for our Vliw machine, with some instructions missing, I2, I6, and I7. We have rearranged the instructions to execute as soon as they possibly can, but ensuring program correctness. Please fill in missing instructions in Table C1. Note, you may not need all the rows.architectureassignmenthelp.com. architectureassignmenthelp.com. Question 7 How many cycles does it take to complete one execution of the loop in Table C1? What is the performance, flop/cycle, of the program? 12 cycles to complete one execution of the loop. 2/12 flops per cycle. Question 8 If you were to software pipeline the Vliw code in Table C1 with the goal of obtaining the smallest software pipelined loop body, how many Vliw instructions would it contain? Ignore the prologue and epilogue, we are only interested in the number of static Vliw instructions in the repeated loop. Hint, you do not need to write the code for the software pipelined version. 3 instructions, because there are 5 memory ops and 5 ALU ops, and we can only issue 2 of those per instruction. Note, one does not need to write the code to get an answer, because the code is highly data parallel and there is no limitation on register usage because of the lack of interlocks. We can keep reading the old value from a register while an instruction that will overwrite it is in flight. It's just a question of how many Vliw instructions are needed to express all the operations. architectureassignmenthelp.com. Question 9 What would be the performance, flop/cycle, of the software pipelined program from question 8? How many iterations of the loop would we have executing at the same time? 2/3 flops per cycle for iterations at a time. Question 10 If we unrolled the loop in Table C1 once, 2 copies total, and then software pipelined it, could that give us better performance than the solution to question 8? Explain. How many flops/cycle can we get? If we unrolled the loop once, we would double the number of memory ops, 5 to 10, and floating point ops, 2 to 4. We don't need to double the number of adds and nes. When we pipeline this unrolled loop, we are constrained by the number of memory units. Now, we need a total of 5 Vliw instructions to do all 10 memory ops. This gives us 4/5 flops per cycle, which gives us better performance than the solution in question 8. Question 11 What is the maximal flops/cycle for this program on this Vliw architecture? Explain. Same as above, 4/5 flops/cycle. We are fully utilizing the memory units, so we can't execute more loops/cycle. architectureassignmenthelp.com. Part D, out-of-order execution with unified physical registers. This problem investigates the operation of a superscalar processor with branch prediction, register renaming, and out-of-order execution. The processor holds all data values in a physical register file and uses a rename table to map from architectural to physical register names. A free list is used to track which physical registers are available for use. A reorder buffer, ROB, contains the bookkeeping information for managing the out-of-order execution, but it does not contain any register data values. These components operate as described in Lecture 5. When a branch instruction is encountered, the processor predicts the outcome and takes a snapshot of the rename table. If a misprediction is detected when the branch instruction later executes, the processor recovers by flushing the incorrect instructions from the ROB, rolling back the next available pointer, updating the free list, and restoring the earlier rename table snapshot. We will investigate the execution of the following code sequence. Assume that there is no branch delay slot. Loop LWR1 0 R2 hashtag load R1 from address in R2 ADI R2 R2 for hashtag increment R2 pointer Bex R1 skip hashtag branch to skip if R1 is 0 add in R3 R3 1 hashtag increment R3 skip bean R2 R4 loop hashtag loop until R2 equals R4. Architecture assignment help.com. Figure D1 on the page after next shows the state of the processor during execution of the given code sequence. An instance of each instruction in the loop has been issued into the ROB. The Bex instruction has been predicted not taken, but none of the instructions have begun execution. In the diagram, old values which are no longer valid are shown in the following format. The rename table snapshots and other bookkeeping information for branch misprediction recovery are not shown. Question 12. Assume that the following events occur in order, though not necessarily in a single cycle. Step 1. The first instruction from the next loop iteration, LW, is written into the ROB. Note that the bean instruction has been predicted taken. Step 2. The second instruction from the next loop iteration, ADI, is written into the ROB. Step 3. The third instruction from the next loop iteration, Bex, is written into the ROB. Step 4. All instructions which are ready after Step 1 execute, write their result to the physical register file, and update the ROB. Note that this step only occurs once. Step 5. As many instructions as possible commit. Architecture assignment help.com. Update figure D1 to reflect the processor state after these events have occurred. Cross out any entries which are no longer valid. Note that the X field should be marked when an instruction executes, and the use field should be cleared when it commits. Be sure to update the next to commit and next available pointers. If the load executes, assume that the data value it retrieves is 0. An extra copy of figure D1 is attached at the end of the midterm in case you need it. If you assumed in Step 4 to propagate the execution of instructions as earlier instructions wake up later ones, we also gave you credit. Architecture assignment help.com. Question 13. Consider 1. A superscalar version of the out-of-order machine described in Part D and 2. A single issue, in-order processor with no branch prediction. Assume that both processors have the same clock frequency and the same latencies for all functional units. Consider the steady-state execution rate of the given loop, assuming that it executes for many iterations. Under what conditions, if any, might the loop in Part D execute at a faster rate on the in-order processor compared to the out-of-order processor? If the out-of-order processor frequently mispredicts either of the branches, it is likely to execute the loop slower than the in-order processor. For this to be true, we must also assume that the branch misprediction penalty of the out-of-order processor is sufficiently longer than the branch resolution delay of the in-order processor. This is likely to be the case. The mispredictions may be due to deficiencies in the out-of-order processor's branch predictor, or the data-dependent branch may be fundamentally unpredictable in nature. Architecture